So good afternoon to all of you. In last lecture we have start with continuous wave modulation. In continuous wave modulation, we have to analyze your various modulation scheme AM, FM and PM in presence of noise. We have to check out what is the behavior of this amplitude modulation scheme and angle modulation scheme in presence of noise. Generally we have to consider this noise is nothing but additive white Gaussian noise. Additive, that means it is going to add in your message signal, desired signal. White, that means it is having the uniform power spectral density for all the frequencies. White Gaussian, it follows the central limit theorem. It follows the central limit theorem. And noise. So in your communication system, generally we have to consider this noise is AWGN. In last lecture, we have seen the AM modulation scheme. AM modulation scheme in presence of AWGN noise. Here we are having the basically two demodulation scheme, that is synchronous detector and envelope detector. In synchronous detector, basically we are trying to plot the relation of output signal to noise ratio with respect to input signal to noise ratio. Input signal to noise ratio. It is generally given as input signal to noise ratio is denoted as gamma. Input signal to noise ratio is given as gamma. We have to establish the relation between output signal to noise ratio to the input signal to noise ratio. For synchronous detector, we will get this output signal to noise ratio S0 divided by N0, that is equal to m square bar divided by m square bar plus a square into gamma. Output signal to noise ratio is related to your input signal to noise ratio. Actually it is a line. We are having 1-to-1 relationship. The slope is given by this equation, that is m square bar. M square bar is nothing but mean square value of your message signal. Then a square is nothing but the peak amplitude of your carrier signal. So here message signal, it's a mean square value, and a, that is the peak amplitude of your message signal, they are related to each other. These two quantities will decide the slope of this line. This line indicates the output signal to noise ratio to the input signal to noise ratio. And secondly, this is 1-to-1 relationship for synchronous detector. For your envelope detector, we are having envelope detector AM with envelope detection. We are having general envelope is given as EI of t, that is equal to EI of t cos of omega ct plus theta of t. In an envelope detector, we are just looking towards the envelope of your message signal. This envelope EI of t, it is given as root a plus m of t EI of t is given as root a plus m of t plus nc of t bracket square plus ns of t square. Similarly, we will get phase envelope, that is theta of t. This will be given as tan inverse ns of t divided by a plus m of t plus nc of t. This is the performance of your envelope detector. This will detect the envelope which will contain the message information plus some carrier information plus your adaptive white Gaussian noise. Here we have to consider AWGN, which is narrowband noise. So in narrowband noise we are having the representation, that is the in-phase component and quadrature component. So message signal is added with your in-phase component and your quadrature component from your narrowband noise. So here we will get the envelope EI of t, that is equal to EI of t. This is the amplitude envelope, and cos omega ct plus theta of t. Theta of t is nothing but giving the phase of this envelope. So it is given as EI of t root a plus m of t plus nc of t. This is the carrier plus message signal plus in phase component of your noise square plus ns of t square. Similarly this phase information. Now here we have to consider two cases. First case, that is small noise case. Here we have to assume that signal is much stronger than noise. So in this case we can see that a plus m of t, here this is the desired part from this envelope. A plus m of t is very much larger than your noise. Here noise, it is having the two component, that means it is having the in phase component nc of t and quadrature component, that is ns of t. So here we can see that a plus m of t is very much larger than these two components from your noise. So by using this assumption we can say that the quadrature component from your noise, we can neglect this quantity. We can neglect this quantity from this envelope. So finally we will get this envelope for small noise case, that is EI of t is equal to a plus m of t plus nc of t. This is the envelope which is true for small noise case, where desired signal a plus m of t, a is the peak amplitude of your carrier signal, plus m of t, this is the message signal, plus nc of t, in phase component of your noise. So here just observe this envelope, out of which this is the desired part a plus m of t, and this is the noise part. So this is added, we can separate out your desired message signal. So here for small noise case we will get this structure. This is a true for this gamma. Up to this one we are having one-to-one relationship. Here for this small noise case we will get signal to noise ratio, output signal to noise ratio, that is equal to m square bar divided by m square bar plus a square into gamma. For small noise case this relation is still exists. Output signal to noise ratio is related to your signal to noise input signal to noise ratio, and this quantity gives the slope. This relation is still exists. Now for the next case where large noise, the noise power is very much larger than your signal power. For this case we can see that a plus m of t, this is the desired part from your message signal and carrier point of view. This is a much smaller than your noise, so we can say that a plus m of t is very much smaller than your noise, that is nc of t and ns of t. So from this envelope we can't neglect this second quantity, that is nc of t. When we derive this equation we will get the envelope, final envelope for this large noise case, that is ei of t, that is equal to en of t plus a plus m of t into cos of theta n of t. E I of t that is equal to E n of t plus a plus m of t multiplied with cos theta n of t. Here we are having the envelope of noise, which is given as, this envelope is given as this one is your noise envelope. This will be given as En of t. Real part is Nc of t, imaginary part Ns of t, that is the quadrature component, and theta n of t, this will give the phase angle for this noise. So here this is the envelope for large noise case where a plus m of t is very much smaller than your noise power. So noise, here we are having the in phase component Nc of t and quadrature component Ns of t from here narrowband noise. So here we will get the envelope that is equal to En of t. This is a totally noisy term plus a plus m of t. This is the desired part from this envelope. It is get multiplied with cos theta n of t. This theta n of t is nothing but the phase angle for this noise, which can be given as tan inverse of Ns of t divided by Nc of t. So here for this envelope, which is for large noise case, we are not able to separate out the desired part. Here desired part is nothing but a plus m of t. This part is get multiplied with your noise term. A plus m of t is get multiplied with cos of theta n of t. So here cos of theta n of t is nothing but the phase angle from your envelope, noise envelope, from your noise envelope. So here envelope detector, this is the case for envelope detector. As we are decreasing the input signal to noise ratio, as we are decreasing the input signal to noise ratio is given as Si divided by Ni. As we are decreasing the input signal to noise ratio, that means noise power is increases. Noise power is increases. As we are increasing the noise power, or as we are decreasing the input signal to noise ratio beyond a certain point, this relation is not valid. This signal to noise ratio, which is related to your input signal to noise ratio, it will give the equation of line with this slope. This line equation is not valid beyond this gamma. So envelope detector gives the performance as good as your synchronous detector, provided this gamma must be greater than this gamma threshold. This gamma threshold. Is it clear to all of you? This is from the last lecture. Now we have to see performance of DSB, SSB in presence of noise. Performance of DSB, SSB in presence of noise. We are having the baseband system. For baseband system, write down for baseband system, that means transmission without modulation. Transmission without modulation. For this system, we have to consider This one is your transmitter part. Here we have to implement this pre-emphasis filter. This one is your medium. Here we have to consider the noise. This one is de-emphasis filter. Your desired part is m of t. This is your message signal get modulated at transmitter part, where we are having the pre-emphasis filter. This message signal which is get modulated is transmitted through medium. Here we have to call it as a channel, which can be represented by this filter Hc of omega. Then it is get received. At receiver point of view, we have to consider your noise is going to add in your system n of t with some power spectral density, and at receiver we are having the de-emphasis filter. So here we have to consider m of t. Write down this m of t. M of t is 0 mean. M of t, which is a message signal, it is a 0 mean wide sense stationary process, capital WSS process, band limited to capital B Hertz. Band limited to capital B Hertz. Then here we have to consider HP of omega. Write down HP of omega, comma HC of omega and HD of omega. These are the ideal low pass filters. These are the ideal low pass filters with the bandwidth of capital B. With the bandwidth of capital B and with magnitude 1. Then noise, write down noise. Noise is 0 mean wide sense stationary, that is capital WSS process, wide Gaussian and white and Gaussian noise process. This noise is having 0 mean, wide sense stationary, Gaussian and white nature or process. These are the characteristics of your noise. Here the power spectral density for this noise, that is given as capital N by 2 for the frequencies which are less than infinity. As this noise is white noise, its power spectral density we are having capital N by 2 for all the frequencies ranging from minus infinity to plus infinity. Here capital N0, this will be given as integration from minus infinity to infinity Sn of f This is the, here this noise is going to input to your de-impedances filter, that is the receiver. Before to the de-emphasis filter, it is having the power spectral density which is a uniform for all the frequencies. This is the power spectral density for your noise, this one. It is going to filter out from the filter which is having the response in this way. So at output we will get this noise power with this band and magnitude of capital N by 2. So over this output noise, we are having the average energy, that is capital N0 is equal to capital NB. And we have to assume that S0 is equal to Si and capital N0 is equal to NB, capital NB. So here output signal to noise ratio S0 by N0, that is equal to Si divided by NB. Generally we require output signal, it should be similar to your input signal. So we have to consider S0 is equal to Si and here N0, that is equal to NB, capital NB. So output signal to noise ratio, that is equal to Si divided by capital NB. This is the output signal to noise ratio for baseband signal. Write down, this is for baseband signal. For double sideband suppress carrier, here we have to consider this message signal m of t root 2 cos omega ct Here we have to consider this is the message signal m of t get modulated. This message signal get modulated with the carrier root 2 cos omega ct. Then it is transmitted over the channel. At receiver, modulated signal m of t is added with your noise, which is AWGN. Here we have to consider this n of t. This n of t is having the quadrature representation. It is having the in phase component and quadrature component. Then it is input to your receiver. This receiver is generally having the band pass filter and demodulator. This band pass filter, which is centered at cutoff frequency fc and bandwidth plus minus capital B. Then it is going to demodulate it with the same carrier root 2 cos omega ct. At this point we will get low pass filter, and finally we will get message signal m of t, which is filtered out from your low pass filter. So here generally we have to analyze the performance of this system at demodulator level. Input to your demodulator, which is given as y of t, it will contain input signal, that is si of t, power over the input signal si of t, this is the process, plus noise ni of t. For this one si of t, we will get the power si, and here we are having ni. Similarly at output we will get y0 naught of t, which will contain the output signal s0 of t and n0 of t. Generally we will desire this m of t, but some noise is added with your message signal. Some noise is added with your message signal. So here this is S0 and capital N0. Noise power or the filter out noise process N0 of t. So here y of t is generally having the signal, that is m of t multiplied with root 2 cos omega ct plus in phase component n of t. This will be given as in phase component and quadrature phase component, which is get filtered out. At this point we will get input signal root 2 cos omega ct and in phase component, which is get input to your low pass filter. So here write down y I of t input to demodulator, y of t is given as root 2 m of t cos omega ct plus ni of t. Here this will be given as root 2 m of t cos omega ct plus nc of t cos omega ct plus or minus ns of t sin omega ct. So here we will get this si, that is expected value of root 2 m of t omega ct square. So here we will get m square of t in bracket 1 plus cos 2 omega ct. So finally we will get m square bar plus 0, that is equal to m square bar. Here we will get yi of t, this is root 2 m of t cos omega ct plus noise part, that is ni of t. This ni of t is having the in-phase component and quadrature component. So here nc of t cos omega ct plus ns of t sin omega ct. Over this one we have to find out the noise signal power or this input signal. So Si is given as expected value of root 2 m of t cos omega ct square. By using your trigonometric representation, we have to write down m square of t in bracket 1 plus cos 2 omega ct. 2 omega ct. So here we will get Si as m square bar plus 0, that is equal to m square bar. This is the signal power which is input to your demodulator. So Si is given as m square bar. Similarly, your Ni, here noise is input to your demodulator. Yeah, this noise is given as Ni, that is equal to 2 NB. That is equal to 2 NB. So input signal to noise ratio will be given as m square bar divided by 2 NB. So at output, write down y0 of t, that is equal to m of t plus root 2 nc of t. Here we have to consider output power, that is m square bar, as initially we have to assume that this is equal to Si, input power, and this n0, that is equal to 1 by 2 n square of t bar is equal to 1 by 2, here 2 into NB, that is equal to NB. So output signal to noise ratio is equal to Si divided by NB, that is equal to gamma. That is equal to Si divided by NB. So this is relation for double sideband suppressed carrier. Output signal to noise ratio, that is equal to Si divided by NB. Output signal to noise ratio is related with three quantities. First one, Si, input signal power. Second one, bandwidth, that is capital B, and next one is your capital N. Next one is your capital N. Just compare this relation with the relation of baseband signal, baseband communication. In baseband communication, we have got it, output signal to noise ratio, that is equal to Si divided by NB. This Si divided by NB is nothing but gamma. Output signal to noise ratio is related as a gamma. So same relation is still exists for this double sideband suppressed carrier. Now we have to look towards, write down SSB suppressed carrier. Now here for single sideband suppressed carrier, same thing, your message signal m of t is get modulated with the carrier 2 cos omega ct. Here 2 and root 2, they are just written for your simplicity. Then it is get filtered out from the SSB filter. Here we will get the signal, that is x of t, get added with your noise n of t. Here n of t is nothing but your AWGN, which is a narrowband noise, which can be represented by your quadrature representation, that is in phase component and quadrature component, which is get input to your receiver. Receiver will contain the two blocks, that is a band pass filter with the center frequency Fc and bandwidth capital B. Then we are having the demodulator block. At demodulator block we are having same carrier, that is 2 cos omega ct. which is given to the low pass filter with the bandwidth capital B hertz, at output we will get y0 of t. Input to your demodulator is given as y of t. Y of t is nothing but we are having this modulated signal plus noise. So here we are having x of t. This is given as m of t multiplied with your cos omega ct plus m cap of t sin omega ct. Here y of t input to your demodulator is nothing but your m of t into cos omega ct plus m cap of t sin omega ct plus your narrowband noise, which can be given as nc of t sin cos omega ct minus ns of t into sin omega ct. So here we will get m of t plus nc of t cos omega ct plus m cap of t minus ns of t into sin omega ct. This is the input to your demodulator. At output, that is y0 of t is equal to m of t plus nc of t. So here power of 2 m of t cos omega ct, power of 2 m of t into cos omega ct, that is equal to 2 m square of t bar, that is the mean square value or the message signal. And here SI, input signal power, SI, that is equal to m square of t bar, that is equal to S naught and capital N0 capital NB. So we will get this ratio, output signal to noise ratio, that is equal to SI divided by NB, that is equal to gamma. So here this relation is still exists, that is output signal to noise ratio is equal to m square bar divided by NB, that is equal to gamma. So for AM modulation, for DSB suppressed carrier, SSB suppressed carrier, output signal to noise ratio, that is equal to gamma, and gamma is given as input signal power to the capital N and capital B, that is the peak amplitude of power spectral density of your noise, which is having the magnitude capital N by 2, this capital N, and B is nothing but the bandwidth of your signal, capital B. Same thing we have to check out for VSB. Write down, for VSB we will get the same relation, that is output signal to noise ratio is equal to gamma, is equal to gamma. Behavior of angle modulated system in presence of noise. Here modulated carrier for this angle modulated system, that is Xc of t, is given as A into cos omega Ct plus phi of t, where capital A and omega C, these are the constant, Write down capital A and capital A and omega c are constant. Phi of t, these are the functions of m of t. Phi of t, these are the functions of m of t. So here we will get xc of t, that is equal to a into cos of theta of t. So here we will get this theta of t, that is equal to omega ct plus phi of t. Here this is the phase information for carrier modulated system. Here we will get omega I instantaneous radian frequency, omega I, this is the instantaneous radian frequency. This is equal to derivative of theta of t. This will be given as omega c plus phi of t. Where phi of t, write down phi of t, that is equal to instantaneous phase deviation. Phi of t is nothing but instantaneous phase deviation of xc of t and this derivative of phi of t, write down next, derivative of phi of t is nothing but instantaneous frequency deviation, of xc of t. Mainly here we are having the two things. This is your phi of t. This is nothing but instantaneous frequency deviation of xc of t. xc of t is nothing but your carrier modulated signal. xc of t is given as a cos theta of t. Here we have to consider that a, that is the amplitude, is a constant and omega c is again constant. Only phi of t is going to change. This phi of t, change in the phi of t is directly or indirectly proportional to your m of t. That means phase information phi of t is related with your message signal. In amplitude modulated signal, we can say that amplitude of your carrier, that is capital A, is related with your message signal m of t. In angle modulated system, we can say that this phi of t is proportional to your m of t. Depending on this one, we will get the two modulation system. Either it is a phase modulation or frequency modulation. This x of t, which is having the angle phi of t, either it is a phase modulated system or frequency modulated system. It will be decided by this phi of t. Phi of t is nothing but instantaneous phase deviation. When we take a derivative of this phi of t, we will get instantaneous frequency deviation. So when we have to take phi of t is equal to constant, we will get omega I is equal to omega c. For phi of t is equal to constant, we will get omega I is equal to omega c. So here for phase modulation, in phase modulation, whatever the phase of this carrier signal xc of t, that is equal to a cos omega ct plus phi of t, it depends upon your change in your phase. Here this phi of t gives the instantaneous phase deviation. It will give the instantaneous phase deviation whatever the change in your phase phi of t is related to your message signal m of t. So here we can see that for phase modulation, this phi of t is proportional to m of t. So here we will get this phi of t that is equal to kp m of t. Is it clear? Similarly for your FM, here FM we require some deviation in your frequency. In frequency modulation we can see that whatever the change in your carrier, that is xc of t, which is given as a cos theta of t, change in frequency deviation is proportional to your message signal m of t. So here we will get derivative of this phi of t, derivative of this phi of t is nothing but instantaneous frequency deviation. Is nothing but instantaneous frequency deviation, means small change in your frequency. Small change in your frequency is proportional to message signal m of t. So here this instantaneous frequency deviation, that means derivative of phase deviation phi of t is proportional to m of t. Is proportional to m of t. This is given as, that is equal to kf into m of t. That is equal to kf into m of t. So here this kp and this kf, this kp is nothing but phase deviation constant. Write down, kp is nothing but phase deviation constant. Its unit is radian per unit of m of t. Radian per unit of m of t. Then kf, this is the frequency deviation constant. Frequency deviation constant. Its unit is radian per second per unit of m of t. Radian per second per unit of m of t. From this one we can find out this phi of t is given as kf into integration from 0 to t m of lambda into lambda plus phi of t0. From this frequency deviation we are related with this phi of t. Here phi of t is nothing but integration over this m of t, kf integration over 0 to t m of lambda into d lambda plus phi of t0. Here phi of t0 is nothing but initial phase angle at t0. Write down, phi of t0 is nothing but initial phase angle at t0. And when we consider this t0 is equal to minus infinity, this will gives phi of minus infinity, that is equal to 0. That is equal to 0. So we will get this phi of t is equal to kf integration from 0 to t m of lambda into d lambda.